This is SAT Math, Section 16. SAT Math, Section 16 deals with functions and their graphs. Anybody who has ever looked at an SAT knows that functions are a gigantically important concept for the SAT. They show up all over the place on every single test, and they show up in a lot of different forms. We've already talked about linear functions and quadratic functions and exponential functions in other sections of this manual. There are, however, in addition to those specific kinds of functions, there are a lot of other pieces of information surrounding functions and function graphs that you're going to need to know for this test. We are, as we always do, going to start from the very basics, and we will build from there. So section 16.1 here, function basics and notation. Functions do get a little bit intimidating for students, sometimes simply because of some of the notation involved. It is important to think about functions very simply, and a very simple definition of functions is right here. A function is simply a set of directions that tells you what operations to perform on a given number or a variable. We call that number or variable the input, and we usually represent that input by an x. So again, something goes into a function, the function itself does something to the thing that we put in, and then a result comes out. In the simplest functions, you might have something as simple as, let's just write a little linear function over here like 2x minus 3. So we might say, or ask, what is f of 5? And what that means is we are taking this 5, that is our input, and we are plugging that 5 in on the right-hand side of the equal sign wherever we see our input from the original function. So we're doing 2 times 5 minus 3. This is the set of directions. This is the set of directions that tells us what to do to the input. We are being told to multiply the input by 2 and then subtract 3 from that product. So 2 times 5 minus 3 is 7. So again, a 5 goes in, the function does some stuff to that 5, a 7 comes out. And that's what we're going to look at right now in terms of the presentation and parts of a function. So a bunch of different parts of a function. We have the function name. Usually functions are named f, g, or h. Entirely possible, though, that you will see, maybe a profit function or a revenue function on this test. You do not have to have an f, a g, or an h. You can have really any letter representing a function. You then will have the input, and the input is the thing inside parentheses. That is extremely important. Always remember that your input, which is usually going to be an x, sometimes it's going to be a t on this test, t for time, but it could be an n. It really could be any variable that College Board decides to put in those parentheses. The input is always going to be inside the parentheses right to the right of the function name. And obviously, f of x is by far the most common form that we see functions taking, both on this test and in school. In terms of what is to the right of the equal sign, so again, we'll have f of x or r of n or p of x to the left. That will obviously, again, include the function name and the input. But to the right of the equal sign, we will have the expression that contains those directions that we just talked about, the operations to perform on that input that we're going to throw into the function. You've got to keep in mind that we have a few different ways of referring to what comes out of a function or what is to the right of an equal sign in function notation. We can call that the output. We can call it the function's value. We can call it the y value. We could also obviously call it the f of x value when we have f of x equals a bunch of stuff. Obviously, whatever is over here equals f of x. So you might even want to add that here, or f of x. So again, we can call it the output. We can call it the value of the function. We can call it the y value. We can call it f of x. So down here, we illustrate all of this using a quadratic function as an example. So again, we have the function name, we have the input inside parentheses next to the function name. Over to the right of the equal sign, we have the the output, or the value of f, or the y value, or the f of x value. Again, this is the set of instructions telling us what to do to the input. We're going to square the input, we're going to multiply the input squared by 2, and we're going to add 3. And the name of the game on the vast majority of, especially the simpler, let's say the simpler function questions, is substitution. Usually what we are going to do is we are going to take whatever is in this position, which again is the input or x position, and we are going to be substituting what is in that position into the right-hand side of the equal sign wherever the input, again the x, appears. So if there were a 3 in here, a 3 would be going in over here. If there were a n in here, an n would be going in over here. Whatever is in parentheses is going in on the right-hand side of the equal sign into the set of instructions. That is what functions will generally look like. We are going to run through a bunch of examples basically illustrating all the different ways that College Board likes to test functions, and the first and definitely the simplest way that College Board will test functions is input to output. In other words, we will be given an x value, and we will need to know the or calculate the y or f of x value. Again, remember that that is synonymous with saying that we would be finding the value of the function. By the way, this is also known as evaluating the function at a particular x value. You may hear me use that word, evaluate the function. So in example 1, most juniors, seniors, even sophomores should be very familiar with how to do these fairly basic input to output questions. So I would recommend pausing the video and doing example 1 on your own. In example 1, we have a function. Again, it is a quadratic function. It's the one we were just looking at, I believe. Yeah, this one's a little different, but similar. We have a quadratic function. How do I know it's a quadratic function? Well, because I've got an x squared there. Keep in mind, one more time, this notation is no different from that notation. F of x and y are pretty much synonymous. When we graph functions on the xy plane, we graph the value of f of x, the value of the function, as the y coordinates. Obviously, we graph the x values as the x coordinates. So we've got this function x squared minus 3x, and we need to determine the following. I'm going to go ahead and circle that, and I'm going to circle this. So first things first, example 1a, we've got to determine the value of f of 3. So what do? Again, name of the game is substitution. Now, just so that we can get very proficient and comfortable with how this all works, what I'm going to do is I'm going to make placeholders. I'm going to sort of turn that x just into a empty parentheses right now. And what that's going to do for me is, you know, over here in parentheses, I have a 3. It's just going to tell me, it's going to tell my brain that, all right, wherever I see that x is just a set of parentheses, where now I have a 3 in the set of parentheses on the left, which means I need to put a 3 in the set of parentheses on the right. Do I need to blank out the x's with these parentheses? No, I don't, but it's actually not a bad practice, especially when you're just getting used to doing function questions, even the most basic ones. So what do I have here? I cannot use a calculator in this case, so I have 9 minus 9. That's a tough one, and I get 0. F of negative 1. Now, this is where it becomes extremely important to be using those sets of parentheses. When we have negatives, and we are squaring those negatives, or we're multiplying those negatives by other negatives, there is a very high chance of, or a very high possibility of, careless mistakes. So this is yet another reason, I'm going to circle this, by the way, this is yet another reason it might be a good idea to get into that habit of drawing parentheses where your x's are, and then just substituting the input that's on the left-hand side into those parentheses. So negative 1 squared, of course, is positive 1. Negative 3 times negative 1 is going to be positive 3, and 1 plus 3, of course, is 4. So f of negative 1 is 4. So again, when we evaluate the function f at an x value or input value of 3, we get out a 0. That is the result. Again, this could be y equals 0. It could be f of 3, or even f of x equals 0. And then when we evaluate at an x value of negative 1, we get a function value of 4. It is important for you, since College Board is fond of mixing and matching concepts, of integrating concepts. It would be a good idea to be able to look at example 1a here and see that what we've got going on is, because this is a polynomial function, 3 is a 0 of this function. When we throw in 3 and we get 0, what this means is that, again, x equals 3 is a 0 of the function. It also means that 3 comma 0 is going to be an x-intercept when this function is graphed on the xy plane. It also means that x minus 3 is a factor of this function, and we should actually be able to see that, because if we were to factor x squared minus 3x, we pull out an x, and we are left with x times x minus 3. So there is that linear factor, which we can get either from factoring the quadratic itself or by knowing that 3 is a 0 of this function, which is what we determined here. So again, probably a good idea to be able to look at functions, know what type of function you're dealing with, in this case a quadratic, and know the significance of what happens when you evaluate the function at certain values of x. At the top of the next page, you are also going to have some questions. You're going to run into some questions where the input is not numeric, rather it will be a variable or an expression. And again, the key here is just substitution. We just take whatever is in the parentheses and we throw whatever is in parentheses in for the x on the right hand side of the equal sign. So when we have f of n, we're not doing anything different. In fact, again, I'm going to draw those parentheses. Let me leave that blank for now. I'm going to fill that in with an n in a moment. But again, remember, wherever I have those parentheses is wherever I had an x, but the x is no longer an x, it's an n. So the n is going in for those x's, and cleaning this up, I just get n squared minus 3n. If I had an expression like a plus 2, I've got a binomial here in my parentheses. Well, again, name of the game is substitution. I'm going to blank out those x's with parentheses, and then I'm going to fill in, this should be a square here, and then I'm going to fill in a plus 2 and a plus 2. And what do I want to do here? I'm going to go ahead and FOIL that first part. I actually could factor out an a plus 2 here, like I did with the x before. I'm just going to go ahead and FOIL that first part. So that's going to be I'm going to write this out over here so I don't make any careless mistakes. So that is a plus 2 squared, which is a plus 2 times a plus 2. I've got a squared. I've got a 2a and another 2a. And then I've got the 2's at the end there. So that's plus 4. So this is a squared plus 2a. Let me just go ahead and combine those like terms. Plus 4a plus 4. And then I've got to distribute this negative 3 to those two terms. So that's negative 3a minus 6. And what's all this going to collapse to? A squared 4a minus 3a is just positive a, and then positive 4 minus 6 is negative 2. So that should be, this one was n squared minus 3n, and this one should be a squared plus a minus 2. Again, factoring out the a plus 2 from each of these terms might have been slightly quicker, but I don't care. I like the way that I did it. Anyway, example 3 is a little bit of a joke, but it does speak to the point that I've been making several times, which is that as long as you don't get too freaked out about functions, and remember that in the vast majority of cases, they are all about substitution, all we're doing is we're taking this smiley face, which is our input, and we are squaring that smiley face, and then we are multiplying that smiley face by negative 3. And that's it. So what do we have here? We have smiley face squared minus 3 smiley face. And that's all. Again, a little bit of a joke. You will not see something like that on any of College Board's tests, excuse me. But it is important to understand that really we're just substituting. Another way that College Board may go, sort of the reverse way that they may go, they may give you a y or f of x value, and they may require you to determine what input value produced that output value. So not all that complicated here. All that's happening again is we already have our output value and we have to sort of work backwards to get our input value. So in example, you might want to pause the video and do example 3 on your own. For most of you, this should not be too complicated. So we've got the function f is defined by f of x equals x squared minus 3x. If f of a equals 10 and a is greater than 0, what is the value of a? So again, they're telling us that a is our input, that's like our x value, and 10 is our output, that's what's coming out of the value when we, out of the function when we evaluate the function at this a value, and they want to know what a value is going to produce that 10. So here's what we're going to do. We're going to first write down f of a equals, and again, let's do those parentheses. I'm just going to substitute forgot my square again. I'm going to substitute the a in there. So I just get a squared minus 3a. And again, they are telling me that when a goes into this function, I get out 10. 10 is the output. So that means that a squared minus 3a must yield 10. And everybody who has done section 12 of the manual, everybody who is very familiar with quadratics should be able to see that this is a fairly simple quadratic equation. What am I going to do? I'm going to put it into pure standard form, which is a squared minus 3a minus 10. And that is going to equal 0. And now I'm going to factor this. I could do this using the x method that we talked about in section 12, but I'm going to do this using some simple trial and error because the numbers here are not very difficult. So I know I need a's in those positions, and this 10, that's going to be a 5 and a 2 that will give me that 3. But what do I need? I need a negative 5 and a positive 2. Will that do it? A squared positive 2a minus 5a minus 10. Yes, I'm just foiling that back through to make sure I've gotten what I need. So a minus 5 times a minus 2 equals 0. Remember, by the zero product property, one of these two factors is going to have to equal 0. What value of a will make this factor equal to 0? It will be 5. What value of a will make this factor equal to 0? It will be negative 2. This is irrelevant because they tell me that a is greater than 0. So the value of a must be 5. Is that what they were asking me? Yes, it is. And I am done. So when 5 goes into this function, let's actually check it. F of 5 equals, it's going to be 5 squared minus 3 times 5. What is that? 25 minus 15. And of course, that equals 10, which is what we were supposed to get. So all looks good there. In terms of composite functions, yet another way that College Board will test functions. Composite functions, again, these can be a little bit tricky for students who aren't extremely familiar with functions. In a composite function, what happens is that one function will have another function as its input. So when we look at this first. So notice here we've got the f function outside, and then inside the input position of the f function, we have another function, g. So g of x is one function that is the input of another function, f of x. By the way, these two notations here, f of g of x, and then this f, this tiny little open circle, almost looks like a sort of a lowered degree symbol, or a tiny little 0, whatever you want to call it. This f and then that little open circle g, and then the x, that means exactly the same thing as this. This is f of g of x, and that's how we would say this too, f of g of x. So you may see this notation on the test. This guy here would be f of g of x. This one here would be g of f of x. So the second function after the little open circle will be the input of the first function before the circle. G will be the input of f. So what we generally recommend on these questions is that you approach them one function at a time if you can. If the question is set up in such a way that you can approach these questions one function at a time, inside function first, outside function second, that's the way you should do these. I'll show you in a moment what this looks like. If you feel confident with composite functions, you can pause the video and do example 4 on your own. In example 4, we have the function f defined by x squared minus 3, yet another quadratic function here. And we need to first know or determine what f of 0 is. So what I was talking about in terms of one function at a time, inside function first, is let's just worry about, well, we don't have to worry about it because it's not hard, but let's take care of f of 0 first, right? That's the inside function. The other f is the outside. So they're both the f functions, but one's inside the set of parentheses and one's outside the set of parentheses. So we're going to do f of 0, the inside function first, and of course that's 0 squared minus 3. Remember that 0 squared is just 0. It is not 1. Don't make that mistake. So f of 0 is going to equal 0 minus 3, which is negative 3. So now that negative 3, I know, is the input of the outer f function. So now instead of f of 0, I have f of negative 3, and I do same stuff I've been doing over and over again, and I get negative 3 squared. There's no x here like there was, I believe, on the previous function. It's just a minus 3, just that constant. So negative 3 squared is 9. 9 minus 3 is 6. So f of 0 is 6. When it comes to example 4b, here we have a new function, this g of x function, and now we are being asked for g of f of negative 2. By the way, again, that could be written as gof of negative 2. Same, these notations are equivalent to each other. So we need g of f of negative 2. So again, we're going to do the inside function first. The f function is inside the input position of the g function. So we're going to do f of negative 2. And what is that? That is negative 2 squared minus 3, which equals 4 minus 3, which equals 1. So now I know that what is inside the g function is going to be 1, which means I am just evaluating the g function at 1. So now I'm doing the outer function, my second step. And the g function is this linear function here. So I'm not going to use the f function again. I've got a new function being defined here. So this is negative 2 times 1 plus 2, which is, well, that's neat. We get 0. So again, when it comes to composite functions, don't make too big of a deal about these. They are generally not all that difficult as long as you take them one step at a time. The tougher versions of these questions might involve an algebraic input. In other words, you might not be just substituting a basic, integer number into a function. You might be throwing in some sort of an algebraic expression. Example 5, good example of that. If you want to try it on your own, obviously go ahead and pause the video. In example 5, we've got the functions f and g defined by whatever and whatever. Write an expression for, so we need an equivalent expression for g of f of x. So again, we're not going to do this all that differently. We are going to deal with that inside function. That inside function, which is the f function, is x squared minus 3x. So we're back to that quadratic function here. So that's the inside function. Well, that just means that what we're doing is we are evaluating the outer function, the g function, at an input value of x squared minus 3x. So if you notice, I'm just substituting. I know that f of x, the inside function, because of this definition right here, I know that f of x equals x squared minus 3x. So that x squared minus 3x is being substituted in for the f of x, the stuff inside the g function's input area. And now I'm going to evaluate the g function at this expression. And the way that I do that is, once again, substitution. So I'm parenthesizing out that x, and into that x position, I'm going to put my input. And now I'm just going to do a little bit of basic algebraic cleaning up. I'm going to distribute. So I'm going to do this over here. Negative 2x squared, and negative 2 times negative 3x is positive 6x, and then that plus 2. And that should be my answer. They want g of f of x. Yes, there's the expression. That is going to be the expression for f of g of x. Negative 2x squared plus 6x plus 2. At the top of the next page, we're going to do one more question that's a little bit of a variation on this composite functions theme. and then we will move on. Example 6, you want to try it on your own, pause the video and do so. Example 6, we've got the function f is defined by f of x equals x squared plus 3x. The function r is defined by r equals 2x minus 3. So again, we've got a quadratic and a linear function here, and we need the value of f of 1 minus r of 3. So not a whole lot different here. We're going to do inside stuff first. So let's deal with what's inside these parentheses. This is the outside function is the f function. R is inside the input position of the f function. So let's deal with r of 3 first. That should be relatively easy. Again, just a simple linear function here. That's not supposed to be a 2, that's supposed to be a 3. So all I'm doing is I'm taking the input of the r function, the 3, and I am plugging that input in for x. So I'm getting 2 times 3 minus 3, which is going to be 6 minus 3, which is 3. So now what I have is I have that outer f function, and I'm doing 1 minus 3 because r of 3 was 3. So f of 1 minus 3 is obviously f of negative 2. And again, some substitution here. I am going to do this where I'm plugging that negative 2 into all of the x positions of the f function, x position there, and I'm getting 4 plus negative 6, and of course that is going to be negative 2. Negative 2 is the value of f of 1 minus r of 3. Now, finally, before we get to function graphing, we've got to talk about new functions defined in terms of another function, in terms of an original given function. These questions actually can be a little stumpy for certain students, especially example 7b. Of course, if you want to try what's going on here on your own, pause the video and do so. I'm going to work through it right now. So in example 7, we have the function f defined by f of x equals 2x minus x cubed. Oh, we got a cubic function here. And we need to determine the following. So first, 7a here, we've got the function g. So there's this new function defined by g of x equals f of 2x minus 5. So we can see that the g function is being defined in terms of the original f function, and they want g of 1. So here's how this works. It works exactly the same way as the way we've done every other question up until this point, which is substitution. That 1 in this position is an input or x value, which means that anywhere I see that x on the right-hand side, I need to throw in a 1. So it's as simple as taking the 1 that was in the x position here and throwing that 1 into the x position here. And now all this becomes is f of 2 times 1 minus 5 is going to be 2 minus 5, which is negative 3. So I'm just evaluating f of negative 3. That's all I'm doing here. So what am I going to do? I am going to put that negative 3 into these x's. I will, again, as usual, I will parenthesize them. I do have to be very careful here with that negative and some of these other negatives and these exponents. I just need to be very deliberate in my work. So 2 times negative 3 is negative 6. What am I going to do here? I will cube that negative 3 first and get negative 27. That's negative 3 cubed. And then I am doing negative 6 minus negative 27, which is negative 6 plus 27, which, if I am not mistaken, should be 21. We are not allowed to use a calculator here, so I am getting 21, and I am sticking to it. So that is how we would do something like example 7a. Example 7b, these are definitely some of the trickiest function questions that will appear. Occasionally, you're going to see a function that is defined. So again, what we've got here is we've got the f function. So there's the f function, but we have this new function h. And notice that the input of the h function is not just an x. That's what we tend to see in most other places. That's what we've seen in the preceding examples. Here we have a function whose input is 2x. And like I said, that can throw students for a loop a little bit, but here's how it works. The question is asked, so first of all, we've got h of 2x being defined as f of x, the original f of x function plus 3. And they're asking us for h of 4. Well, remember when we write h of 4, we've got to remember that what is in parentheses here is no longer an x, it's a 2x. So that 4 is a 2x. So 2x now equals 4, which means to get my x, to extract my x, I have to set the 2x equal to 4, then divide by 2, and I get x equals 2. So in order to produce a 4 in here, x must be 2. 2 times 2 is 4. So I know that this h of 4 tells me that my x is 2, which means that the input of the f function over here is just going to be 2. So now I know that h of 4 is going to equal f of 2 plus 3. And of course, with this 2, I can just plug the 2 in for these two x's. So that's 2 times 2 minus 2 cubed. And then, of course, I've got to not drop that 3. Probably a very simple way to make a careless mistake here. Got to make sure I bring down all parts of this equation up here. So I've got 4 minus 8 plus 3. 4 minus 8 is negative 4 plus 3 is going to be negative 1. So h of 4 is going to be negative 1, h being defined in terms of the f function here. So that gives you a good sense of all of the different ways that College Board will tend to test functions. However, these are actually mostly the more basic ways. Yes, example 7 maybe got a little bit more advanced there. The most advanced ways that College Board will tend to test functions will be in terms of function graphs, which we will cover in a subsequent video.